The next periodic table trend that we're going to be discussing is ionization energy. And just as a recap, an ion is a charged atom, and more specifically, a positively charged atom is a cation, and an anion is a negatively charged atom. And I always remember this because in school I got a lot of C pluses and I got a lot of A minuses and not much in between. But another way to remember this that's kind of funny is we've got a cation. Cats, they have paws, and their paws are very positive. Cats are positive. But what ionization energy is we've got, it's the amount of energy required to remove an electron, thus turning the atom into an ion. This last part is not technically part of the definition, but it's going to help us remember. It's going to help us remember the definition. Because if we break apart this word here, we have ionization energy. So it is the energy required to remove an electron. And if we remove an electron from an uncharged atom, it's going to turn it into an ion. So what that means is if we have an atom, it's basically its willingness to give up an electron is going to be related to its ionization energy. Specifically, the higher the energy, the harder it is to remove an electron. So there's a topic we need to cover real quick, very briefly, before we can understand ionization energy, and that is the octet rule. Every atom on the periodic table has a goal in life to get to 8 valence electrons. Every atom, that is, except for these first 5. 1, 2, 3, 4, 5. And we'll discuss why that is. Actually, we can probably think about why that might be. If we recall, the first energy level of any Bohr model can hold up to 2 electrons. So that's why helium is happy with 2, because it can only hold 2 anyway. Hydrogen, if it just adds an electron, it can get to 2. Lithium, if it removes an electron, it can get to 2. Beryllium here, if it removes 2 electrons, it can get to 2. And then boron, if it removes 3 electrons, a little bit harder to do, but if it removes 3 electrons, it can get to 2. So they're all happy with getting to 2 electrons. But every other element on the periodic table wants to get to 8 valence electrons. And whether their goal for the first 5 is to get to 2 or everything else to get to 8, we call that the octet rule. And oct means 8, so that's how we're going to remember that the goal is to get to 8. Another way that we could remember that is that if we have, back when I was a kid and we had texting, this is before we had emojis. And so we didn't send the actual emoji smiley face. We sent a colon and a parenthesis. But sometimes we were kind of experimenting with things because these emojis were not set in stone. Nobody decided these are the emojis. People just kind of played around with things as they went. And some people, instead of drawing a smiley face like that, they drew it like this. Or they typed it like this on their phones. And so you can kind of turn your head and you see that kind of looks like a smiley face, maybe like sunglasses smiley face too. So that's how the cool kids wrote their smiley faces. But that might help you remember that the octet rule is that every atom wants to get to 8 valence electrons, and that is just the goal in life of every atom. Obviously, atoms are not actually living beings, but let's just play along and think of them as if they are. So they really, really want to get to 8 valence electrons. And so first of all, let's look at these elements here in the 8th column on the periodic table. The elements on the 8th column, they already have 8 valence electrons. They are as happy as can be, couldn't be happier. But if you try to take away one of those valence electrons, it is going to fight with its dear life. It does not want to give away an electron. It just spent its entire life trying to get to 8 valence electrons. It's finally there. It doesn't want to give it away. So they are going to have a very high ionization energy because they already have 8 valence electrons and they do not want to get rid of any of them. They are content with where they're at and they are going to fight for their life to keep all 8 of those electrons, of those valence electrons. These elements here in column 7, we call these the halogens. They have 7 valence electrons. Since they are not quite at 8, some of them just kind of, they might give up and they'll put up a good fight, but they might eventually give up and give away an electron. But it's still really hard to remove an electron from one of these. Here it's a little bit easier, but it's still pretty hard. Here again, a little bit easier, but still fairly hard, etc. But once we get over here to column 3 and over, specifically, let's look at column 1. They have a long way to go to get to 8 valence electrons. So the future is not looking so bright for them to gain electrons to get to 8. So they might just kind of give up and just give away an electron because if somebody tries to take one, they're just like, I'm never going to be able to add 7 electrons, so I might as well just take it. And in fact, these elements here on this first column of the periodic table, they are not only just going to not put up a fight, they're almost going to give away their electrons. These are some of the most reactive elements on the entire periodic table because they are begging to give away an electron. And I will show you why here. So if we're looking over at the 7th column here and we have fluoride, it wants to add an electron so that it can get to 8. If it adds an electron plus 1 electrons, it's going to get to 8. But if we look at sodium, which is on the first column, it's located right here. If we look at sodium, it has 1 electron in its valence shell. So we mentioned that one way that it could get to 8 valence electrons is it could gain 7 electrons. But that's a long way. You got to be pretty motivated to want to cross all the way across the periodic table to get to 8 valence electrons there. So actually, sodium has an easier way to get there. And you might be able to pause the video and think about it. But yeah, go ahead and do that. How can sodium get to 8 valence electrons without adding 7? So if you thought about that, you might say, well, what if sodium, instead of gaining 7 electrons, what happens if it would lose this one? Well, if it loses this one, then this electron shell right here is no longer going to be relevant. It's no longer relevant. We now have sodium with a positive 1 charge. We now have sodium with a positive 1 charge because it lost a negative charge. Now it's left with 1 more positive charges than negative charges. And now, looky here, we've got 8 valence electrons for sodium. With 8 valence electrons, sodium is so happy it has 8 valence electrons. So again, this first row, or this first column here, not only are they they're not going to put up a hard fight, they almost want to give away that electron, because if they give it away, if they can find somebody to take that electron, they will have given up this last outer row, this outer shell, and they have a new outer shell with the happy number of 8 valence electrons. So it looks like we have established here that, and the same thing is going to happen with if we have another element here in the second row. Instead of giving away 1 electron, it's going to give away 2 electrons. And then the third row, instead of giving away 1 electron, it's going to give away 3 electrons. But as you might imagine, it's going to be harder to give away 2 electrons than it is to give away 1. and it's going to be harder to give away 3 than it is 2, etc. So the trend, if you haven't noticed, and maybe pause the video, let's think about the trend. Is the trend going to be right to left or left to right in the amount of energy required to remove an electron? Is it going to require more energy to remove an electron the further we go to the right or the further we go to the left? And the answer is going to be the further we go to the right on the periodic table, the higher the ionization energy is. The higher the amount of energy required to remove an electron and turn the atom into an ion. Now, next we're going to discuss what about as we go up and down? Is the ionization energy going to increase as we go up or as we go down? So let's think about that one here. And I drew cesium here to help make that point. So if I have sodium versus cesium, and I'm going to redraw my sodium as a uncharged sodium. So give me 1 second. All right, so sodium with, it's still going to have 8 electrons there. It'll just have 1 electron here, though. So sodium's back to 11 electrons, and we got an uncharged sodium there. And imagine that the energy levels are going to be equally spaced. In cesium, they're not closer together than they are in sodium necessarily. I was just drawing it a lot smaller here so that I could fit cesium here, because cesium has 6 energy levels, so I just had to draw it smaller so that it all fits. But don't think of it as being almost equal in size as sodium. It's actually a lot bigger than sodium. So let's think about, we are talking about the ionization energy, whether it's going to increase going up or down. So cesium is going to help us make that determination. So let's think about the distance that this electron here is versus this electron is from the nucleus in sodium, and the attraction that this electron has to its nucleus here versus this electron to sodium's nucleus. So which is going to have a stronger attraction? The outermost electron in cesium to its nucleus, or the outermost electron of sodium to its nucleus? So I like to think of the nucleus as a magnet, and because opposites attract, the positive charge of a proton is going to attract the negative charge of electrons and pull those electrons in. But if the electron's not too far from the nucleus, as it is in sodium, at least comparatively to cesium, if the electron's not too far from the nucleus, there's going to be a strong attraction for that electron so that it doesn't leave or get taken from something else. So sodium it only has 3 energy levels, and so it's going to have a stronger pull on this electron than this electron will have, or the nucleus of cesium will have on this outermost electron here, because it has 6 energy levels away instead of just 3. Furthermore, think about, we just said that opposites attract. So the positive charge of the proton is going to attract to the negative charge of the electron. But what about if they're not opposites? What about the same charges? Do they attract or do they repel? So if I have, so looking at it specifically, we have the negative charges of this electron. How are they going to react with the negative charges of these electrons, and the negative charges of these electrons, and these electrons, and these electrons, and these electrons? How are they all going to react to one another? Well, if something has the same charge as something else, it's going to repel. So we actually have this shielding effect here, to where the electrons in the inner shells are going to shield that outermost electron from being able to be fully attracted to the nucleus. So the electron shielding that's going on there is going to block this outermost electron from being fully attracted to that nucleus. They're actually going to help push away the electron. And because of that, that means that not only is this electron going to be less strongly attracted to the nucleus because it's further away, but also we have the effect of the inner electrons pushing it away. So therefore, for multiple reasons, for both of those reasons, cesium it's going to be easier to remove this electron from cesium than it is to remove this electron from sodium. Again, cesium, this valence electron in cesium is both further away and it has more electrons in between it and the nucleus to further reduce the attraction to the nucleus. So what does that mean in terms of ionization energy? Does that mean that cesium is going to have a higher ionization energy than sodium or a lower ionization energy than sodium? Remember that ionization energy is the amount of energy required to remove an electron. Is it going to take more or less energy to remove this outermost electron from cesium or this outermost electron from sodium? It's going to take less energy to remove the electron from cesium because not only is it on the first row of the first column of the periodic table to where it kind of wants to give it away, but also it's really far from the nucleus and it has a very big shielding effect from these other electrons to where it's going to really be taken away pretty easily. So just from those examples, we know that cesium right here has a lower ionization energy than sodium. So sodium has a higher ionization energy. So what does that mean? Assuming that trend is going to hold true for every column, and it will, the ionization energy is going to increase as we go up in energy levels. Up on the periodic table. So the higher up on the periodic table, the higher the ionization energy. So let's draw a line or an arrow for the overall trend of what ionization energy is on the periodic table. So the overall trend for ionization energy on the periodic table is going to be, as we go up and to the right, ionization energy is going to increase. So up and to the right. And so specifically, the elements with the highest ionization energy are going to be these ones up here on the right, top right. And the elements with the lowest ionization energy are going to be elements located here on the bottom left. So hopefully that was helpful covering ionization energy. It's an important trend on the periodic table it's going to come back and be extra important once we start talking about chemical reactions and reactivity of elements. We kind of gave a little preview of that, but a very important trend for the periodic table.